Okay, hi everyone. I want to take this video to introduce the concept of orders on sets, which are also called orderings. These are pretty important concepts throughout a lot of mathematics, and in particular, they're important if we want to understand the statement of Zorn's lemma, which is used in the proof that every vector space has a basis. So the goal of this sequence of videos is to eventually explain that proof, to prove that every vector space has at least one basis, which we know how to do in the finite dimensional case, but in the infinite dimensional case requires a lot more mathematical subtlety, really. So that's the eventual goal. But for now, we have to talk about orders on sets. So the idea of an order is it's supposed to generalize the notion of some of the orderings we're very familiar with. The standard orderings on the naturals, the standard orderings on the real numbers, the standard orderings on the integers, etc. So let me explain what I mean by that. By an order or an ordering, what I'm going to mean is some knowledge about which elements of a set are quote-unquote bigger than elements of the same other elements of that set. So for two natural numbers, if you give me 4 and 5, I know 5 is the bigger one, right? 5 is bigger than 4. And if you give me two rational numbers, 27/15 versus 100/12 or something, I know that 100/12 is bigger than 27/15. So any two numbers you give me from any one of these sets, I can tell you which one is bigger. Notably, this isn't something we have for C, for example, the complex numbers. There's no good notion of when one complex number is bigger than another. You could try to, define something, but they won't be particularly nice orders, or any kind of way you try to make sense of a complex number being bigger than another complex number won't have all the nice properties we like for orderings. So we'll try to explain that as well today. All right, so in the same way that vector spaces, our definition of a vector space comes from observing that classically, traditionally, we have these vectors that are ordered tuples, where the scalar multiplication and addition are just operations that we found useful when dealing with vectors. We observed that all these vector spaces that we used, it happened to be the case that the vectors were tuples, and the scalar multiplication was just scaling each component, and the addition was just adding the components. But really, it didn't matter what the vectors were. It didn't matter what the addition was. It didn't matter what scalar multiplication was. All that mattered was that this set of vectors existed, and it's possible to add two vectors together, and it's possible to scale a vector by a scalar, and those things play nicely with each other, for example, via distributivity. All those things, those were like the key ingredients of the idea of a vector space. That's what allows you to do linear algebra. It wasn't really the fact that the vectors were tuples. That wasn't a necessary detail. The important thing was that you had a set of vectors, and you had these operations, and they satisfied some axioms. So in a similar way for us, it's not going to be necessary that we're ordering a set of numbers. Here, all the orderings we're familiar with are on numbers, right? One number is bigger than another number. But for us, we're going to be able to have some notion of what it means to order any set. At the same time, the idea of an ordering is going to become more loose. It's not just going to be only these 4 examples that I've discussed so far. We're going to have the ability to describe just kind of a general framework for what it should mean to be able to compare objects in a set, to be able to order the objects in a set. So it's going to be some structure that satisfies some axioms. Let me first say what the axioms are, and then I'll say what the data of an ordering actually is. But the axioms are just stuff we observe in practice, in the same way we observed, in practice that adding vectors together should be commutative. That's one of the axioms for vector spaces now. So let's do the same kind of observation for orderings. The 3 properties we're going to want to have are, first of all, we're going to want A less than or equal to A. So that's saying any object is less than or equal to itself. That makes sense, because less than or equal should allow for being equal. So that's something we want of any kind of notion of ordering. A second thing should be that if A is less than or equal to B, and B is less than or equal to A, then we can conclude that A equals B. So this makes sense for numbers as well, right? If A is less than or equal to B and B is less than or equal to A, then they actually have to be exactly the same. So okay, that makes sense. And let's look at our third property, which is going to be another familiar one. If I have that A is less than or equal to B, and B is now less than or equal to some set C, then, in fact, A is less than or equal to C. So, for example, 1 is less than or equal to 2, 2 is less than or equal to 3, and 1 is less than or equal to 3. This is a transitive property of orderings. So, in fact, all these axioms have names. Let me just list them out. This first one is called reflexivity. The second one is called antisymmetry. And the third one is called transitivity. Okay, so it isn't really so important, just good to know this is common terminology. Okay, so that's these are the three axioms we're going to have for our ordering. These are going to be kind of the things that, where if we want to say, I've ordered this set, whatever ordering scheme you've come up with better satisfy these properties. So that if I ask you some questions, if you happen to have three objects, A, B, and C, and I ask you, is A less than or equal to B, and you say yes, and I ask you, is B less than or equal to C, and you say yes, then it better be the case that if I ask you, is A less than or equal to C, you better tell me, yes, A is less than or equal to C, or else this wouldn't be what seems like a consistent idea of an ordering to us. So that's where these axioms are coming from. Okay, so now that we have the axioms, it's a good question to ask. What actually do these axioms mean? What is an ordering? It's something that should satisfy these axioms, but what does it even mean to satisfy these axioms? What does the less than symbol mean here, right? What does this less than or equal to symbol actually mean? So let me be more precise about what I mean here. What we want to have is we want an ordering to be basically a collection of answers to questions of the form, is A less than or equal to B? So an ordering should be able to tell us, if I have an ordering on a set, it should be able to tell us for any two elements of that set, is the first one less than or equal to the second one? And is the second one less than or equal to the first one? It should be able to answer those questions for us. So how do we describe some data that can answer those questions for us? Here's the way we do it. So let me write down the formal definition. Let X be a set in ordering. Let me actually use the more precise term. A partial order is the technical term on X is a set R such that R is a subset of A Cartesian product A, and three axioms hold. These are going to be our ordering axioms. So the first axiom is the reflexivity axiom. Remember that said it should be the case that A is less than or equal to A. Well, let me try to explain what R is supposed to tell us. We're defining an order to be a subset of A cross A. I'm sorry. I was calling this set X. So a subset of X cross X. I got confused there. Okay, so we're defining an order to be such a subset. It's a subset of X cross X, which means it's a set of ordered pairs, right? The elements of R are ordered pairs where both elements of the ordered pair come from the set X, but they might be different elements, and they come in an order. Okay, so the idea for us, let me stick that before we even say the axioms. The idea is that the way R tells us what things are less than other things is by giving us the pairs where the first thing is less than or equal to the second thing. So let me write that out. x1, x2 is in R. I'm going to put quote-unquote means x1 less than or equal to x2. So let me explain what I mean by means in quotes. Here I'm saying that x1 less than or equal to x2 doesn't yet have a well-defined meaning for us. We had this vague intuition that it should satisfy some axioms. Like once we can define what this means, then it should satisfy some properties. So how do I define what this notation means, x1 less than or equal to x2? Our definition for that notation is going to be x that is going to be, like, this is true when x1 comma x2 is an element of this set R. So the set R is reporting for us what are the pairs of things where the first thing is less than or equal to the second thing. That's the idea of what R tells us. And so, so I'll have another note on this after the definition. But let me write out the reflexive property, which remember said that everything should be less than or equal to itself. What does that look like when I'm thinking about the set R for my order? Well, it means everything should be less than or equal to itself, so that element, comma, itself, should be an element of this ordering. So this should say, for all A in X, A comma A is in R. That's our first axiom, and this is the reflexivity. Remember that A comma A in R is what we mean by A is less than or equal to A with respect to this ordering. Okay. Property 2 was antisymmetry, which said that if I have any two elements of my set and they're both less than or equal to each other, then in fact they're equal. So let me write out what that would mean. A less than or equal to B means that A comma B is in R, and B less than or equal to A means that B comma A is in R. This little symbol here means and. That little caret, kind of. Let me draw that more clearly. That's just shorthand. I really should just write and. And B comma A is in R. Okay, if we have both of these premises, then I can deduce A equals B. That should be for any two objects. If one of them is greater than or equal to the other, and that's true both ways, A is less than or equal to B and B is less than or equal to A, then A equals B. That's antisymmetry. Oh. Antisymmetry. Okay, and finally the third property is transitivity. That was the one that said that if A is less than or equal to B and B is less than or equal to C, then A is less than or equal to C. So let me write out what that means. For all A, B, C, if A comma B is in R, and B comma C is in R, then A comma C is in R. That is transitivity. Okay, now that we've written the definition in this form, the definition of a partial order on a set is completely unambiguous, right? This is just saying a partial order is a subset of the Cartesian product of the set with itself, satisfying these three precise mathematical conditions. So it's no longer a question of what exactly did we mean by it should satisfy these axioms. Now we have a real definition. So let me say one note first. So maybe two notes even. Remark. In this situation, so if R is a partial order on X, it's a subset of X cross X which satisfies these three axioms, then people often write ARB when they mean A comma B is an element of R. So the idea is that A comma B is an element of R is supposed to say A is less than or equal to R with respect to this partial order. So that's very wordy. And so it would be nice to kind of shorten that to be like A less than or equal to B. Just you could write that as shorthand, right, for A comma B and R. That's easy enough, except that we care about the fact that this depends on the partial order, right? Saying A comma B and R is saying that A is less than or equal to B with respect to this particular partial order structure. And there could be other partial orders on the same set where that's not true. In fact, there definitely are partial orders on the set where that's not true. So we need to be careful that when we're writing down some shorthand for this notation, we want to capture the thing R. So instead, we write ARB. And this is just shorthand for A comma B and R, just a more convenient way to write A is less than or equal to R with respect to this partial order. And so, as a result, we often use the symbol less than or equal to denote the standard ordering on n or z or r or q, etc. If you have a really standard ordering, I guess these 4 examples that we talked about, we use this symbol less than or equal to denote that partial order. So let me actually be precise about that. The standard partial ordering is the set of a comma b in this set, right? N or z or q or r, whichever one is appropriate, such that a is less than or equal to b in the standard sense. So like our traditional notion of less than or equal to, I'm just capturing the set of all pairs a comma b where a is less than or equal to b. And that's the standard ordering. So that's that set that we call less than or equal to. So we use this symbol, usually reserved for some kind of relationship between numbers, to actually now be a mathematical object. It's the set of all ordered pairs a comma b where a is less than or equal to b. And that lets us write a less than or equal to b, because that's just shorthand for a comma b in less than, which is equivalent to saying that a is less than or equal to b. Right? What does it mean for a comma b to be an element of less than? It means that a comma b is in, it should be n squared or z squared or q squared or r squared. Sorry about that. It means that a comma b is an ordered pair of one of these kinds of numbers, such that a is less than or equal to b. Okay, so now this notation that we have using a, r, b to denote a comma b and r coincides with our standard notation for less than or equal to when we have the convention that we denote that standard ordering by the symbol less than or equal to. The less than or equal to symbol now stands for this set of pairs that is the standard ordering on the corresponding set of numbers. Okay, so that was a little long-winded. That's the remark, I guess. So, with that out of the way, I want to talk about another example of a partial order that we've seen before that isn't one of these standard orderings that we talked about on numbers. So example. What we're going to do here is we're going to let S be any set. And this is going to be a set of sets. So the elements of S are also going to be sets themselves. Just to, as a side note, this is actually always the case in all of mathematics. The typical way to formalize math and make rigorous formal definitions for every single thing all the way down, the typical way people do that is to define everything to be a certain kind of set. Everything is formally defined as a particular set, and we have fancy ways to interpret these sets as telling us about numbers or topological spaces or things like that, but everything ultimately gets encoded as sets. So this is really always the case if you're given a set in standard mathematics. It's a set of sets, because every object is a set, every mathematical object ever, and as a result, any element of any set is some mathematical object. It's also formally encoded as a set. Okay, but we don't have that like logical framework. We don't understand yet how to break every aspect of mathematics down into the bare bones of sets. So for now, let's just say that S is a set of sets. It's just some set where the elements of S also have to be sets. Okay. Then S has a partial order which is called less than or equal to, defined by less than or equal to is the set of all a comma b in S cross S, such that for all a in A, A is in B. Remember, this is precisely what it means to say that A is a subset of B. Okay. So all that's happening here, this is really defined in a very similar way to this standard ordering that we had, the standard partial order on the natural numbers. This partial order, called subset or equal to, is defined as the set of pairs of sets where the first set is a subset of the second set. And so let me just quickly note, this is at least a subset of S cross S. So it satisfies that part of the definition up here. It has to be a subset of the set cross itself. And it needs to satisfy these three axioms. So let me explain what those three axioms would say in this case. In this case, the three axioms are, well, the axioms would mean that A is a subset of A for all A, that A is a subset of B, and B is a subset of A, implies A equals B. That would be the second thing they say. And the third thing they say is that if A is a subset of B and B is a subset of C, then A is a subset of C. And this should be for all sets A, B, and C, elements of S. Okay, but it's actually easy to check that all three of these things are true. I highly recommend you prove it as an exercise if that's not just immediately obvious. Even if it is immediately obvious, it's probably good to just write down the proof of like this thing here, this transitivity one, just to make sure it really is obvious. Okay, so but assuming you've done that proof, because I absolutely believe you can do it, it just takes doing it once. We know that this is a partial order on the set S, and this is an interesting partial order on, like I said, really any set. Any set is partially ordered by subset containment. It's another way to say this. So that's a really useful partial order in many contexts. And this is really going to be the one that we use when we use Zorn's lemma eventually to prove that every vector space has a basis. So that'll come much later, but it's very important to be aware of this partial order. It's going to be crucial for the story. Okay, I think that's where I want to stop this video. Just to recap from the top, we had this idea of standard orderings on number systems, right? Natural numbers, integers, rationals, or real numbers. We had this idea of when, like, that some numbers are less than or equal to other numbers, and that this relationship of being less than or equal to is something that satisfies a bunch of these three properties in every example. So that's the term partial order that we've defined. A partial order is just this thing that lets us test these three axioms. It answers. It tells us like which pairs of things should be, it's a bunch of pairs that tell us which things should be smaller than or equal to which other things. For any two things, I ask, if I have A and B, I ask, is A comma B inside this set of ordered pairs? And if A comma B is in the set of ordered pairs, then that set of ordered pairs, that partial order, the partial order is telling me that the first thing in that set of ordered pairs is less than or equal to, or the first thing in that ordered pair is less than or equal to the second thing in that ordered pair. So that's what it means to have a partial order, is precisely that. Precisely that it satisfies these three axioms we stated up here, just rephrased in this formal sense, where the partial order says that one thing is less than another if the ordered pair is in the partial order as a set. Okay. Then we talked about notation for a little bit. This is just kind of like some interesting mathematical convention that was tricked around to work out nicely so that our notation makes sense with this new formal definition. And finally, we talked about this important example of a partial order that isn't on numbers, just on any set of sets. So for example, the set of subsets of n is a perfectly good set that's partially ordered by subset containment. And this partial order is just defined by one set being contained in another. And so that's another good example of how we could order the elements of a set, is if they're contained inside each other as subsets. So that's another kind of ordering we could have. All right. So that's all I wanted to talk about for now. In the next video, we'll see maybe some differences between this partial order, this new partial order we described, and the standard partial orders we had before. While they do share those axioms in common, and they're both very important, there are some crucial differences. So we'll talk about those, and we'll gear up for a discussion of total orders and eventually moving to Zorn's lemma.